So hi everyone, this is the first of the Landau-Ginzburg seminars. Landau-Ginzburg is a pair of physicists. We won't be talking about physics, but the original inspiration for studying this bicategory comes from mathematical physics, and hence the name. Mathematicians often refer to it by a slightly different name, so I'll talk about that in a moment. But I want to start kind of fairly elementary by making an argument for one of the reasons why this particular bicategory is of some interest. So recall that a category has objects and morphisms. Between them. So e.g. sets and functions. And I'm going to spend, like, the running theme of this seminar will be a comparison between this situation, sets and functions, and the sort of nature of that. So, for example, how can you compare two functions, or how do you compose functions? I'll be comparing that to a higher categorical setting. So, the first observation to make about functions is that two functions are either equal or not. But in general, there is no finer relation that you can consider on functions. A bicategory, on the other hand, has objects, one morphisms, and two morphisms. So the objects and one morphisms behave quite like a category, but there's additional information in the two morphisms, which are between one morphisms. And this additional structure means that, for example, in the case of categories, functors and natural transformations, those are the objects, one morphisms, and two morphisms of a bicategory. So in that situation, you can have a richer set of relations between functors than you can between functions. For example, two functors can be isomorphic, different but the same. And there's much more you can say. So the whole point is that one morphisms form a category. And a category is a richer object than a set. I won't say what I mean by relations, but for example, you can have one functor being a subobject of another functor, and that happens all the time. Alright, so that's an abstract categorical statement. We'll be focused in this series of seminars on a very particular bicategory.
Dan?
Yeah.
Is there no finer relation between two morphisms than equality inside a two category?
Yeah, that's
or
right.
Bicategory?
But you can talk about three categories and fix that. Yeah.
Yeah, makes sense.
So one of the things, I guess it's the primary goal of the seminar, is to give a detailed construction of a bicategory called LG, called either the, well, maybe I'll just say it. It's either called the bicategory of Landau-Ginzburg models, or the bicategory of isolated hypersurface singularities. So the objects, one morphisms and two morphisms of this bicategory have a geometric origin. And in that sense, it's rather different in flavor from categories, functors, and natural transformations. So it's a very concrete bicategory. And in that concrete bicategory, we're going to be looking at a sort of specific instance of this general pattern of there being interesting relations between one morphisms, and interesting in this situation. One of the threads of the seminar series will be the relation between that additional structure between one morphisms and computation. Okay, so that's the broad overview. We'll be talking about this bicategory, giving a construction of it, and discussing its relation to, well, various different things, including computation. So now let me actually start to give a very rough first definition of this bicategory.
Dan, sorry, just let me check quickly. Toma did want to come to this, but he had another meeting, so he wanted it to be recorded. Is this being recorded?
It is, yeah.
Ah, okay, good. Yes, he sends his apologies.
That'll be $49.95.
So you are turning a profit after all. I think I can go back into Discord and find the sentence where you said you weren't going to do that.
The objects of... I'll just define... So this bicategory, there's one copy... Well, there's a bicategory per base ring. I'll just start by talking about the version which is defined for the complex numbers, because it's the easiest to understand. So the objects of LGC are complex polynomials, say f, in any number of variables. Okay, so the objects are very simple, just polynomials, all polynomials, including 0. Well, sorry, not all polynomials. They need to satisfy a condition I'll specify in a moment, but 0 is among them, and it's not a complicated condition. With the property that the zeros of the following vector field, which assigns to a point in Cn the gradient of f, right, assigns to each point of Cn that vector. The zeros of that vector field, that is the n tuples of complex numbers where all the partial derivatives vanish, that these are isolated. That is, they're individual points separated from every other such individual point by, say, open neighborhoods. That's it. Such polynomials are called potentials. So those are the objects. What are the one-morphisms? Well, I'm not going to define all of them because it's a bit complicated, but the one-morphisms from a potential f to a potential g are, let's just say, closed subsets in the Zariski topology. You don't really need to know what that is for the moment, but I can't say subvariety, I can't say subscheme, so I think maybe this is the easiest thing to say. Closed subsets of the zero set of G minus F. I.e., so X is
Can I ask a silly question?
Yeah, go ahead.
Is this potential definition for someone who hasn't done vector calculus in a while? Is it the same idea as the usual vector calculus one?
Yeah, that's right. Yeah, there's no...
So no
the fact
zero
that
curl somehow corresponds to this?
I'm not sure what you mean.
No, that's the wrong thing. I just remember the definition is somehow not the same, but I forget exactly how.
Oh, okay. Yeah, if you're referring to the fact that it's over C rather than R, I mean, for the purposes of what we're doing, there's no difference. Yeah, I mean, if you like, you can even just ignore the occurrence of vector field here. I just want to consider all the points where all the partial derivatives vanish. Let's call it P. Yep. So X is a subset of, I'm going to use V for vanishing. So what this means is take a polynomial and take all the points where it's 0. Now, in this case, G and F depend on different sets of variables, right? So the vanishing of G minus F needs to be, so if we suppose that F had n variables and G had m variables, then to feed a point into both F and G, I need m plus n complex numbers, let's say PQ. So the vanishing locus are all pairs, PQ, such that G of Q minus F of P is 0. So those are equal. Okay, so that's some potentially very complicated subset of Cn cross Cm. And X is a closed subset in some topology. It's what's called the Zariski topology, but I don't really want to define that right now. I'll simply say where X is cut out of Cn cross Cm by polynomial equations. So X itself is the vanishing set of some set of polynomial equations. And that's what it means to be closed in the Zariski topology. Okay, so that's...
So Dan,
yeah.
Do you have this intuition sitting inside your head when you're looking at the more general context? So thinking about potentials as these polynomials that satisfy the conditions involving the, exactness of the relevant causal complex, etc. And one morphism is matrix factorizations. Are these the ideas that those concepts generalize, or is there more to the more general theoretical story than that?
Not really. This is what? Technically not quite true, right? The real definition is more complicated, but conceptually it's no more than this. This is not a dummies version. And this is how I think about it, to answer your question.
That's so interesting. So is this what you've written for potential, is that equivalent in the case, in the case of the complex numbers? Is this condition here sufficient to satisfy all the other conditions?
Yeah, that's I mean, the sufficiency is a remark after the definition in our paper. Maybe I should comment. So much of what we're going to be discussing comes from a paper with my friend Niels. Titled Adjoints and Defects in Landau-Ginzburg Models. There's a link on the seminar webpage. We'll also be talking about work by many other people, of course, but this is what I'm talking about right now. So there, the definition of the bicategory is sort of given in more technical language, but the notion of potential over C is really not, I would say, I forget if it's equivalent. I think it probably is. So, for example, when Niels writes papers about our bicategory, he just defines potentials to be this, because this is the only example that physicists care about. Now, to define it properly over more general base rings is more involved. I mean, that's why the definition in that paper is more intimidating, because it works over any ring. But yeah, partly it's kind of a red herring. It's not as complicated as it may appear.
So is that true of matrix factorizations as well? The definition of a matrix factorization in this context becomes equivalent to just these closed subsets. So like the closed subsets of this vanishing set are in bijection with matrix factorizations or something, or up to homotopy or something.
Not bijection, but any such closed subset by its coordinate ring gives you an object of the derived category, and that's equivalent, or quotient of it is equivalent to a matrix factorization category. So you can, in some way that may be actually very complicated in general, assign to any closed subset X, as I've considered it here, a matrix factorization. But that assignment is actually highly non-trivial, so that's why sort of the definition works at the level of the concrete object rather than this more geometric picture.
I see.
Yeah.
Okay, that's helpful.
Yeah, but I'll give some examples of exactly that translation in a moment. Okay, moving on. Okay, so example. Yeah, maybe I'll just leave it. I could have made some more comments on the definition of one morphisms there. I didn't define two morphisms, you'll notice, right? But that's okay. I'll just keep going. So those are the objects in one morphisms of a bicategory, so I claim. Now, it's not obvious how to take that geometric data and define composition and find a unit and check associativity and all the other things you'd have to do to check that something is a bicategory. And that's why the seminar won't be over in 2 hours. It will take longer than that. But that's the basic picture. And here is the simplest possible example. So let's take two polynomials, z squared and w squared, and consider their difference, g minus f. Well, so that's w squared minus z squared, which is w minus z, w plus z. Okay, what does the vanishing set of this polynomial look like? I'm going to call this w. So this is the difference, right? So remember that in this bicategory that I'm claiming exists, an arrow from the polynomial f, which is z squared, to the polynomial w squared, which is another object, an arrow like that is some closed subset of the vanishing locus of the difference, right? So what is the vanishing locus? Maybe I won't introduce this letter yet. What is the vanishing locus of g minus f? Well, it's the set of all pairs. In this case, p and q are just numbers, such that when you apply g minus f to that pair, you get 0. Well, looking at the factorization of g minus f, we can see that that is in exactly the set of pairs where w is equal to z, that's the vanishing locus of the first factor, So P equals Q. So this is the vanishing locus of W minus Z, union the vanishing locus of W plus Z. Okay, so this vanishing locus looks like this. And I'm going to call this first part x1 and the second part x2. Okay, so this whole thing is... Okay, so what are the arrows from z squared to w squared? Well, they're closed subsets of this vanishing locus, and well, there's 3 of them on the board, at least, right? There are 3 irreducible ones on the board that aren't made up of smaller pieces, namely x1, x2, and the origin itself. Okay, so closed subsets x1, x2, and the origin are all one morphisms from z squared w squared in LG. Now, hopefully it's occurred to you that it would be very strange if z squared and w squared were really different objects of LG. I mean, they're the same polynomial, they just got a different variable. Surely those aren't different objects. Well, they are different objects in the same way that, you know, star and star with a hat are different sets, right? But they're bijective. So the polynomials z squared and w squared are different objects, but they're isomorphic to one another. And indeed, x1 is that isomorphism. Okay, so we have what is an isomorphism. We'll discuss that at some point.
Can I just ask, you said those are 3 closed subsets. Are there more in the Zariski topology, or is that actually it?
The whole thing is closed, for example. Now, there are plenty more points, right? So here is 2, 2. That set is the vanishing of the polynomials z equals 2 and w equals 2, so it's certainly Zariski closed. So there are plenty more points here. I guess why am I focused on these 3 in particular? Well, it would be a digression to explain, but somehow those are the ones I want to talk about. There's good reasons to do that, but I shouldn't have given the impression that those are it. Yeah. So for example, there's points. Those would be Zariski closed, and they're not on that list. Yep. Okay. Just check how I'm doing for time. I have like 4 computers around me and none of them showing the time. Just a second. All right. Okay, so there's a few things I can say at this point. So those are examples of one morphisms in LG. Well, I guess so what, right? So you can organize, I can make this definition. To even convince you this is of interest, I have to start talking about how you might compose these things, right? What would it mean, for example, to compose x1 and the sort of version of x1 that, maybe I'll draw it up here. Suppose I had u squared. Well, between w and u, I can use the same construction, right? I can define an x1 prime and an x2 prime that look exactly the same as what's on the board. They just have w and u in them instead of z and w. And then there's the question of, well, how would I compose say x2 and x2 prime. What would that mean? Well, it should be something like a closed subset of the vanishing locus of u squared minus z squared, according to my definition. How would I come up with such a thing? Okay, so that's sort of where, I mean, the geometric interest is not in this definition, it's in the rule of composition. So I want to get to that. But before I do that, I said this is a bicategory of isolated hypersurface singularities. And I want to explain what all three of those words mean before we move on. Okay. Yeah, I guess I'll do that on the next book. Okay, I'll stick with the same example. So g minus f, which was w squared minus z squared. And what is its gradient? Well, that's the vector, which is dw. I mean, I'll write this out because I need to choose which letter goes first. And I'm choosing w, well, little w. That's 2w minus 2z. Okay, so that vector vanishes if and only if w equals z equals 0. So what does that mean geometrically? Well, so there's the vanishing locus of w. Suppose we're out, so here's the origin where nabla w is 0. Suppose we're out here at a point P, which is AB, not equal to 0. Well, proceeding in this way, I stay where w is 0, right? That's a level set of w. So you're used to the idea that traveling along the gradient will be a direction of steepest descent, right? So the vector, which is the gradient evaluated at AB, is normal to the vanishing locus of W. Well, so notice we can actually evaluate this, right? That's just 2a minus 2b. So let me draw a few examples in. So if I'm over here, that vector will point up like that. If I'm over here, the vector will point in like that. You should look at the vector and verify you understand why that is. Now, you should remind yourself what this function looks like if you look at its graph, right? If I look at the real points of the zero set and of the graph of w, well, this is a saddle, right? This x that I've drawn here is the sort of bridle that sits. Oh, bridle? You don't put a bridle on a saddle. It is the saddle, I guess, itself, maybe, or I give up on this analogy already. So what direction does it increase? Well, wherever these arrows are pointing, right? So up here is high. And then...
Can you label your axes, please, Dan?
Oh, sure, yeah.
That would be very helpful.
Yeah, that commits me to choosing labels. I chose W there, yeah. Thanks. And this is getting low down here, right? So that hopefully loads the picture of a saddle into your head. Okay, so those green vectors that I've drawn, together with the vector that just goes along the lines, which is WZ, or AB, I guess. that pair give local coordinates at every point P, which is not 0. So for example, at this point, if I zoom in on this point, what I'm looking at is just a line sitting in C2. Right, so that's a copy of C sitting inside C2. That's the definition of what a submanifold looks like locally. Right? So at such a point P, the vanishing locus looks like a submanifold, but that's not true at all at the origin. At the origin, you can't view the zero locus as looking like a lower dimensional copy of C, power of C, sitting inside C2. It doesn't look like that, no matter how closely you look at 0. So the vanishing locus is not a submanifold near 0. And that's closely related to the fact that that's where the gradient vanishes, because if it's non-vanishing, you can pull this trick and construct local coordinates that make it a submanifold. Okay, so the pair, so maybe I'll make this a more general definition. So I want to define hypersurface singularity. I'll return to the first board to do so. Okay, so definition. A point P in the vanishing locus of some W is a singularity of W if the gradient of W vanishes at P. So near P, the set, let's say, is not a submanifold of Cn, where n is the number of variables in W. So it's a point which doesn't look like a submanifold. That's one way to
Zane,
think.
can I just ask something?
Yep.
I've always been confused about this. Maybe it's obvious, but how could it possibly be a submanifold? Like, what topology are you working in? If we have a line embedded in Cn under the Zariski topology, then that line is not Hausdorff. That's correct, right? And so therefore it can't possibly be a submanifold.
Yeah, I mean, you shouldn't. Yeah, when I say submanifold, I don't mean keeping the Zariski topology and forgetting that you came from a subset of Cn defined by polynomial equations. In the geometry I'm discussing here, somehow the polynomials come first, and if I give you a polynomial, you're free to equip the zero set with any number of topologies. The Zariski topology is one, but I can also just use the ordinary subspace topology. And when I say something is a submanifold or not, I'm referring to making use of the ordinary topology as a subset of Cn.
That makes sense to me, but I thought it was just a little strange to have that kind of like dancing between topologies, kind of. But that's okay.
That's part of the music of algebraic geometry. Yeah.
Okay.
Okay.
It's easier to swallow when you say the polynomials come first. I guess that makes sense.
Yeah. Yeah. Okay, the pair. So that definition says a point is a singularity of a polynomial. Right? The pair consisting of the point and the polynomial is called a hypersurface singularity. I've explained what I mean by singularity. Hypersurface just because there's one function, W. So if you cut out a subset of Cn with more than one equation, well, unless you can find a way to write it as being cut out by a single equation, it's not a hypersurface. So a hypersurface is a subset of Cn cut out by one equation. That's all. Okay, so that's a hypersurface singularity. And so example, we talked about one. The origin and w squared minus z squared is a hypersurface singularity, and it's isolated because none of the other points on the zero locus of w squared minus z squared near zero are singularities. In fact, none of the other ones are singularities, because this x, everywhere except for the origin, the zero locus does look like a submanifold there. So this here is a lonely singularity, and that's the kind of thing we want to have objects of LG, isolated hypersurface singularities. Okay. Now I want to start getting towards composition, which is what's interesting in a category or by category. But I need to have a more interesting supply of examples first. So I'm going to take this very simple example and make it more interesting. And it'll be interesting because I'll tell you how to think about arbitrary permutations as examples of one-morphisms, that is, as examples of closed subsets of some difference. Okay, so here's my second example. I'll label this permutations. So consider the following polynomial. I'll keep calling it W. It's in two n variables. Half of them I refer to as y's and half of them as x's. N here is greater than or equal to 1. Okay, so clearly if n equals 1, that's just the example I presented. This is a potential. Good exercise. Right? Take the partial derivatives, check the only place where they all vanish and w is 0 is at the origin. And notice that its form means that it's talking about, I mean, if you view this from the point of LG, then here I have the sum of x squares, and here I have the sum of y squares, and closed subsets of the vanishing locus of this W are exactly the kind of things that can live as arrows or one-morphisms between those two sums of squares. Okay? Now for every permutation of n letters, I'm going to construct just such a closed subset. And it's easy to see how to do that if I just rearrange the polynomial, right? So, I mean, this thing just looks like a sum of squares, and I'm free to just regroup them, right? And the regrouping I choose is to have y1 squared be with x sigma 1 squared, dot dot dot, yn squared minus x sigma n squared. Well, you'll agree that's the same thing, and then I can just do this factorization of differences of squares. Okay, so now can we look at that and see a closed subset of the vanishing locus of W? I'm not going to draw a picture of the entire vanishing locus or claim to classify the components or anything like that. You can do that, but that's not what I want to focus on. I just want to produce some interesting closed subsets. Well, how do you get a closed subset, say X, of the vanishing locus of W? You need to give a collection of points where W vanishes. How should you make W vanish? Well, have a look at this expression. I just need to find a point, a collection of points where all of those summands vanish, and then W itself will vanish. And to make each of those summands vanish, well, I can make either one of those factors vanish, and maybe for the sake of simplicity, I'll just focus on making the first factor vanish. Okay, so I can look at all the points where those first factors all vanish. But that's the graph of the permutation itself, right? So consider, I'll write gamma, because that's how you write a graph. And that's the following. So A1 through AN, and then A sigma 1 through A sigma n. That lives in Cn cross Cn. And I take all collections of all sequences of n points. Well, you'll agree that that is a subset, right? Because if I take such a tuple and evaluate yi minus x sigma I on it, well, yi is going to pick out, it's the projection which picks out a sigma I, and x sigma I will pick out the sigma ith ai, which is a sigma I, and so that difference will be 0. Okay, so W will vanish on all of those points, and that's for each sigma. And that set is literally the graph, right? So this is the graph of the function from Cn to Cn, which actually does that permutation. Okay. It's closed because it's cut out by... notice that it is exactly the vanishing locus of those polynomials, right? And hence, as the vanishing locus of polynomials is closed in the Zariski topology. So this gives me my example of one morphisms from this sum of squares to itself, essentially, right? I can think about it as just being endo one morphisms, arrows from that object of LG to itself. And as a picture, here's a picture of the vanishing locus. Here are all these different components, and they all intersect at 0. And there's a component that's special, which corresponds to the identity permutation. I'll call it E. Right? And that's just the diagonal. That's
Interrupt.
Yeah.
You said that graph there is actually the entire vanishing locus.
Mm-hmm.
But we were just talking about the first factors. Like, is it just like symmetric? If you think about, like, if we wanted to make each of these summands, or these things being added up all 0, you can sort of make choices whether you make the first one vanish or the second one.
Yeah, exactly. So let me give a more general definition. So I'll introduce some more notation and take into account Billy's suggestion there.
But what Dan wrote was the graph of the permutation, not the graph of W. Is that the point of
Right,
confusion?
but didn't you say at the end it's equal to the vanishing?
Yeah, but he's only taken the first factors.
Oh, right, okay.
Yeah.
Okay.
Okay. Well, those choices means giving you n bits, right? I either take the left factor or the right factor. And then I can just put in here minus 1 to the B1. I guess I should take 0 or 1. I can stick signs in there. and then exactly the same story is true. Right.
Mm-hmm.
But yeah, that's right. And they're
Does that change the picture? Or
no, they're just also there.
okay. But those are genuinely new sections.
That's
not-
right. Yeah, they're new.
Yeah.
Yeah, somehow this is the hint of supersymmetry. I'll just make that cryptic comment and run away.
Thanks.
Okay, so, well, that gives you a richer set of examples. And now I want to start showing how to organize that collection of examples in several different ways. One of them is geometric, the other is sort of algebraic with ideals, and the other is algebraic with modules. And that will be the bridge that we need to start getting more towards commutative algebra and the kinds of... at the moment, I've presented one-morphisms in LG as these purely geometric things, closed subsets of some vanishing locus. But it's not easy to see what's interesting about composition if you stick purely at the level of the geometry. So we need more algebra. And that's what I'm about to do. Well, let me think. I could just define composition. No, I'll stick with the original plan. Okay, so... okay, so in the setting of this example, okay, so let me give 3 columns should be enough, I think. I'm going to draw the same thing 3 different ways. So in the first, I'm going to consider, well, yeah, I kind of want this picture. Right, so this was the picture we had. There's the identity component. There's some more interesting one, and off they go. So it's a very simple geometry, right? It's a configuration of lines and a point. Okay, so what is the partially ordered set of inclusion relations between these components? Well, 0 sits inside all these different components. I'm saying components because they are the irreducible components of the vanishing locus, if you know what that means. And the whole space is Cn cross Cn. But there's something else I can draw in this picture, which is the vanishing locus of W itself, right? In which all of these gammas are contained. That was the point. Okay, that in the picture below is just the whole thing. So this is the geometric picture. There's an algebraic picture which is about ideals or collections of functions, and in that picture 0 corresponds to the maximal ideal, which is generated by all the xi's and all the yi's, and contained in that is, let me call it IE, I sigma, and the ideal generated by W. So here I sigma just means the thing whose vanishing locus I wrote at the end of the previous board, I guess, maybe the one before. So that is the ideal generated by these equations. That's an ideal in the ring which has all the x variables and all the y variables. Okay. W is an element. of those ideals. To convince you of that, I just need to drag your attention back to the board over here. Look at this formula, right? This formula literally writes W as a sum of products of things that are the generators of that ideal. So that expression shows you that W is in that ideal. Right? Okay.
Dan, could you remind me what IE is?
Yeah, so IE is the special case of this I sigma, where sigma is E, the identity permutation.
Oh, okay.
But so it's just yi minus xi. Yeah. Okay, so W is contained in those ideals, which means the ideal generated by W is contained in them, and then at the bottom we have the zero ideal. And the way to pass from that picture to that picture is to take vanishing loci, and the reverse is something I don't need to explain. Okay, and the third way of thinking about, this is all talking about this one diagram, right? The third way of talking about it is to talk about modules. To do this, we take the polynomial ring and we mod out by whatever ideal we saw in the middle column. So we take this quotient, we take that quotient, we take this quotient, and so on. The exercise right now is to figure out which direction I'm going to draw these lines. Do they go up the page or down the page? I is contained in J.
I'm going to guess down the page, because usually map out of a quotient to like the thing at the bottom.
Yeah. Okay, so if we have if I take CXY and I mod out by J, J is some ideal. Well, if I is contained in J, then this map here will kill I, right? Because it sends everything in I into J, and J is 0 in the quotient. So that means that if I had this other quotient by I, that's a co-kernel, right? So this is the universal map out of CXY that kills I. So if this thing over here also kills I, there must be a map like that. One way to say that is it's well defined, because two things are equal here if their difference is in I, but if their difference is in I, it's also in J, so it's well defined just to send an equivalence class to itself, so to speak, over there. Okay, so the maps between quotients follows the direction of the inclusions. So it's the same as the middle column.
Yeah, I was wrong.
that's
You are correct for giving it a go, Billy.
Yeah.
Exactly. I'll give you a Roblox badge. Okay. Okay, so I'll just annotate this picture a little bit. This here is just C, but as a module, the xi's and the yi's act as 0. These things here are isomorphic. They're also algebras, and they're isomorphic as algebras to a one-dimensional thing, and that's because they're the coordinate rings of those components, and those components are one-dimensional, right? And this thing here, well, this is a complicated algebra, possibly. We don't present that in any simpler way. Okay. Well, they're modules over what? These are all CXY modules. They're actually algebras. But notice this quotient here. So that quotient is the coordinate ring of the vanishing locus. Doesn't matter if you don't know what that is. It's just some quotient of that polynomial ring. Now, since there's these maps of algebras, that means that everything that's sort of upstream from that guy there, these things are all modules over that ring. Which is another way of saying that you can take any polynomial from the quotient by W and just multiply it by a residue class here, and the result will be well defined because of the fact that W is in that ideal. So you can define the
You
action.
didn't write the coordinate ring.
I didn't write. Oh, there's an arrow sitting there. What? You mean this one?
Did you mean you've just written all CXY modules? Do you mean
Oh,
all
thank you.
CXY?
Yeah, thanks. Yeah. That's what I meant to say. Thanks. Okay. So that's how to think about permutations in these three different ways. Now I'm ready to talk about composition, I think. What's the time? Oh, I'm over time. Nobody stopped me. I think that's a reasonable place to stop anyway. So maybe I'll make one more comment and then we can pick this up next time. So I'll just move over to the next board. Okay, so I can take the bounded derived category of finitely generated modules over this thing. So this is finitely generated modules and bounded complexes of them. It doesn't really matter what that is, but that's some category. And it's a category in which all those closed subsets I was talking about live as objects. Right, or rather their coordinate rings live as objects. That is, if I take CXY modulo that ideal, that's an honest object of that category. Okay, so that's a way to look at this diagram and think about all those lines. I mean, gamma sigma somehow is like the same thing as I sigma, and I sigma is the same thing as this quotient, this module. That's how algebraic geometers see the world. And this particular avatar of that geometric object lives in that category. Now, when I say that in LG there's that gamma sigma is a one morphism, that this permutation somehow has a representation as a one morphism from a sum of squares to another sum of squares, that's because the morphisms, the one morphisms in LG, well, I won't say really, but include not just these sort of patently geometric objects, but also objects of categories like T. T is the thing at the top of the board. So we're going to extend the set of things we consider as one morphisms from these simple geometric things to more complicated things. That's sort of necessary to set up the bicategory correctly, but it's important not to lose sight of the geometric origin. And once we've done that, we can sort of do the world's most complicated composition of permutations. So I'll explain that next time. That is how to take a permutation, think about it as an arrow in this bicategory, and then compose it with another permutation. And you can use an insane amount of machinery to just compose those two functions, but hopefully in an interesting way. Okay, I'll leave it at that, and I'm eating into Eleanor's time, so maybe I'm just going to be Soviet about it and reject all questions. So let's migrate over to the other world.
Thanks, Dan.
Yeah. Thanks.
We go this way. Yeah. Okay.